Hello and welcome to a new tutorial in your YouTube channel Science and Engineering, and today we continue with electric circuits, the Wheatstone bridge. So what is a Wheatstone bridge and what is the principle of the operation and what are the advantages of the Wheatstone bridge? This is what we'll see now. So a Wheatstone bridge, as you can see in this circuit, is used to measure the electrical resistance of an unknown component here. This could be a resistance in case we are talking about DC circuits, or even an impedance if we are talking about AC circuits. So this Wheatstone bridge has two legs. The first leg, or the first arm, is consisting of the resistors R1 and R2, and the second leg consists of the resistors R3 and our unknown resistor here, the Rx. And the principle or the concept here is that if we can balance these two legs here, the ABC and ADC, and this means, by balancing, we mean that the voltage difference, the potential difference between the points D and B would be zero. So if we put here a voltmeter or a galvanometer, we will not see any difference in the voltage difference between these 2 points, in the potential difference, or a current passing in from the node D to the node B. So let's see this. If we start by analyzing this balancing thing, we would say that, okay, in order that we don't have a potential difference between these 2 points D and B, if we put here a galvanometer, so a galvanometer is a device to detect the direction of a current. So if there is a current flow from the point D to the point B, it will deflect in this direction, and if there is a current flow from the point B to the point D, it will deflect in the other direction. So if we start distributing the current, here's the total current. It will be divided into I1 and I3, and then the I1 will go to this node. It will be divided into I2 and IG. Here the I3 will be divided into IX, and it will get the IG from here, Kirchhoff current law. So in the balance condition, we would see that the no current will be flowing from the point or from the node D to the node B. So this means that IG will be equal to 0, and I1 is simply equals to I2, and here also I3 is simply equal to IX. This also implies that there is no potential difference between these 2 points D and B, which means that the voltage at D is equal to the voltage at B. So if we rewrite this, we know that this is a common point for these two resistors, Rx and R2. R2 is a variable resistor, and here is actually we are using a potentiometer, and by adjusting the value of this potentiometer, the R2, we come to this balance condition. So we will try here to change the value of R2 until we get a zero current flow in this galvanometer, or a zero potential difference between these 2 points here. So the voltage across this DC or the R2 resistor at the balance condition would be exactly equal to the voltage drop across the Rx. And the voltage drop, then this point A is a common for the resistors R3 and R1. And if these 2 points exactly have the same potential difference, this means also that the voltage drop across the resistor R1 will be exactly equal to the voltage drop across the resistor R3. And this is what we see here. So if we get this formula. Now, substituting for the voltage by the currents and resistors, we come to this formula, and we know that I1 is simply equal to I2, and I3 is equal to Ix in case of the balance condition. So we come to this formula where we can define or find the value of the unknown resistor, or the unknown component if it was an impedance, for example, using this formula. Now, as we can see that it's a very simple way to find this resistor in case of the balanced condition. Now, if we go to the unbalanced condition, where the current will flow from the point D to the point B, or from B to D, because there is a potential difference actually between these 2 points. It is not anymore zero potential difference. This means that the current I1 is not equal to I2, and IG is not anymore 0. I3 is also not equal to IX. So in this case, we can use the voltage divider rule, which we have discussed in one of our previous tutorials, and we come to this point. Now, if we, for the unbalanced condition here, put a voltmeter between these 2 points here, and we assume that this voltmeter is a kind of an ideal voltmeter that will withdraw a very small current here that can be ignored, then we can do a voltage divider analysis here, and we can say that the voltage drop in this branch, which is equal to the R2 divided by the sum of the 2 resistors here, R1 plus R2, multiplied by the supplied voltage. This gives me the voltage drop at the voltage at this node D, since this one is 0, so I get the voltage at that point. The difference between this voltage here and the voltage level at that point, and at that point it will be also, if this current is ignored, then we can say it is simply equal to Rx divided by the sum of these 2 resistors here, Rx plus R3, multiplied by the Vs. This is the voltage divider rule that we have discussed in the previous tutorial. The difference between these things here is actually the voltage, the potential difference between these 2 points. In case we put here a resistance, then a current will flow from here. From this we can come to, if we rearrange it and try to get X as an explicit function of these resistors, we come to that point. Now, as you can see here in this formula here for this Rx, it's a bit complicated than this one in case of the unbalanced Wheatstone bridge. And we can see that if we use a very high resistance here, the R3, at this resistor, a high resistance here, R3, and we keep R1, R2 constant, this means that this term, because R3 here is in the denominator here, so this term will be small. So this Wheatstone bridge will be less sensitive to the changes in Rx, because the whole thing is being divided by a very large resistance. And this gives us the first information that this Wheatstone bridge is better used for small resistances rather than big resistance. It becomes less and less sensitive. Now, if we see the relation between the voltage difference between the nodes D and B, the Vg, or the voltage measured by the voltmeter here, as a relation to changes in the Rx here is represented by Rp, we can see that at the point where we come to the balanced condition, the voltage will be exactly equal to 0. And if we deviate a little bit by adjusting this R2, this is the variable resistance here, then we are deviating from this balanced condition and we are going to an unbalanced condition. If you can also see that in this region here, the curve is can be considered as a linear curve, and this is also one of the advantages of the Wheatstone bridge, that it can be considered in a certain range as a linear bridge, which gives us a very good advantage in the measurements. And by the way, I forgot, this can be used if this Rx is, for example, this resistance is a sensor, which is a temperature sensor, for example, or a strain sensor measuring the pressure, for example, then any changes in this Rx value here will take us from this imbalanced condition and will cause here a little change in the voltage here above the 0 level here, and this can be detected and gives us indication of the temperature that is being measured or the strain that is being measured. So this is one of the uses of this thing. So usually this Rx is a kind of a sensor measuring temperature or pressure or whatever strains needed to be measured. Now the whole thing looks very nice, and if we somebody can think, okay, why do we need to use this Wheatstone bridge? We can use a voltage divider bridge, and if this Rx here is called R2, but I can use a potentiometer here and use a voltage divider concept, very easy. And by changing this potentiometer or this resistor here, I come to a point where I reach the half voltage here. When I reach the half voltage here, it means that these two resistors are equal, and this is a known scale for me. So for example, if this is a 10 volt and this is 2 kilo ohm, and I keep adjusting this resistor from 1 kilo ohm, 1.1, 1.2, the time I reach the 2 kilo ohms, then I measure here 5 volts, and now I can read on the scale here 2 kilo ohms, and then I have detected this resistor. And this is actually comes from the voltage divider rule. So the V out is just the R2 divided by the sum of these two resistors multiplied by the supply voltage, and this can give us the relation R2 is just equal to R1. Now this relation is very much more simple and easy as compared to the one in the Wheatstone bridge. And if we look also at the curve here, we can see that we arrive to the half voltage here at the point of equilibrium when this resistor is exactly equal to half the value of this resistor. So it seems that this voltage divider bridge is actually much easier to use and understand than the Wheatstone bridge. So what would be the advantage, or what is the advantage actually of the Wheatstone bridge over this voltage divider bridge, or even simply over a multimeter, an ohm meter, which can be used directly to measure this the value of this resistance, or an oscilloscope, or whatever meters that we use today. This is actually a very good point, because if we look here at this voltage divider bridge, we see that the value that we are trying to measure, the Rx or the R2 here in this case, is a function of R1. Okay, R1 is our potentiometer resistance, which we are changing, so we know this value, and Vin is our supply voltage, so okay. But V out is the voltage that we measure here across this unknown resistor, and this is actually subject to some errors that could happen in the voltmeter here. So if this voltmeter has an error in its measuring, if it is not the very good quality or the fancy voltmeter, then there is an error in the measurement, and this error here in the measurement will be reflected on the correct value that we are reading here. So if this voltmeter, for example, is draining some current from the circuit, then when it reads actually 5 volts here at the point when this thing here is reading 5 volts, it will not give us the correct value. There will be an error here in the resistance value. So this takes us to the advantage actually of the Wheatstone bridge. At the Wheatstone bridge, actually, if you go a little bit back, so if we go here in the Wheatstone bridge, we see that the unknown resistance that we are trying to measure actually is function of known resistors, the R1, the R2 on our potentiometer scale, and the R3. Okay, so this is all known to us, and the supply voltage, which is also known to us. So at the point where we achieve the balance here between these 2 points, then the Vg actually becomes 0, and we come to this form. So as you can see, this is not a function of any voltage measured, so there is no error due to the measurement device. This makes this bridge very accurate at the point of when it is balanced, as compared to the voltage divider bridge, or even measuring with a standard multimeter or something like that. So a very good advantage of this Wheatstone bridge is that I can use the bridge itself to calibrate the voltmeter here. So if this bridge is balanced such that I have this ratios of the resistance here, and I can still read some potential difference through my voltmeter here. This means that this is an error in the voltmeter and I can calibrate my voltmeter. Or if I have here an ammeter and I can measure a very small current here in the ammeter, then it means that I can calibrate also my ammeter and remove this offset in or the error, the measurement error from my ammeter. So it is actually used to calibrate the voltmeter, the ammeter, when it is in the balanced condition. It can also be interfaced with many circuits, and this voltage here can be connected also. This can be also connected to an operational amplifier here, and this VG here is amplified and used to see amplify small differences in the potential difference between these 2 points. Now again, if this thing is not balanced, then we still have a voltage here, VG, and the device error will be also there, same like the voltage divider, but the advantage is when we are in the balanced state, then we don't have this device error. If we look here at this circuit, Wheatstone bridge, and this is our unknown resistor here, and here is our variable resistor which we will try to adjust. It's a potentiometer. We're trying to adjust until we achieve the balance. So at the point of balance, the potential difference between these 2 points D and B should be 0, and no current will be flowing in this resistor R5, and the voltage difference or the voltage drop across this resistor will be 0. And just by looking, we have said that the condition for being balanced is that the ratio of the resistor R2 to R1 must be equal to Rx to R3, or R3 to Rx, so easier R3 to Rx, so 6 divided by 2 is 3, so the ratio should be 3. So we can see that, okay, this should be also, the ratio should be also 3. So this means that the balance point here would be at 1 kilo ohm. And if we look at the simulation results here, by changing the value of R2, we see that exactly at the point 1 kilo ohm here, we come to a 0 voltage. So there is no potential difference between the points D and P, and this is our balanced condition for the Wheatstone bridge. Now, a very important remark about the Wheatstone bridge here. If we are doing some circuit analysis for this circuit, and we are asked, for example, to calculate the total current here in this circuit, for example, or for example the total resistance here of this circuit, then if we look at this circuit, we would see that, okay, we just have no simple series parallel resistors, because we have this resistor here R5. But if we are smart enough to notice that, okay, the ratio here between these two resistors, 6 and 2 is 3, and if this is 1, then the ratio would be also 3. So by these equal ratios means that we have the setup of the Wheatstone bridge at the balanced condition. This implies that no current will be flowing in this branch and no voltage difference between these two branches. So this means that this resistor R5 as if it is not existing, and I can remove it from the circuit, and this makes the analysis very easy, because then I will be just having these two resistors in series, and the sum will be in parallel with the sum of these two resistors, which are also here in series together, and this simplifies our analysis. So that's it about the Wheatstone bridge, and I hope you enjoyed the tutorial, and until then, thank you.